Okay, if you love mapping out the unknown, you are absolutely in for a treat today. Just imagine redrawing our map of the universe, but not by launching some shiny new telescope. Instead, we're doing it by unleashing a completely new kind of digital brain on the data we already have. Today, in this explainer, we're diving deep into exactly how artificial intelligence is stepping up to conquer the cosmos and catalog exoplanets.
Seriously though, how on Earth, or I guess off-Earth, do you discover over 100 planets in a single massive sweep? For decades, confirming even a single exoplanet was this incredibly painstaking years-long endeavor of just constantly double-checking data. But a fascinating recent study published in the monthly notices of the Royal Astronomical Society holds the answer to this massive mystery, and it literally flips traditional methods upside down.
Okay, let's dive into this. Here's our roadmap for today. First up, a gigantic space challenge. Second, AI to the rescue. Third, strange and rare worlds. And finally, we'll look at the future of exploration.
All right, starting right off with Section 1, a gigantic space challenge. So, we're all pretty familiar with the transit method, right? NASA's TESS satellite stares at stars, just waiting for that tiny fractional dip in light as a planet passes in front. But the challenge here isn't the method itself, it's the sheer volume. TESS has collected continuous data for 4 straight years. We are talking about millions upon millions of light curves. It's kind of like looking for a gnat flying in front of a stadium spotlight from 100 miles away, all hidden within this massive hurricane of data. And this brilliantly illustrates the problem. Take the Kepler-11 system, which was observed back in 2010. You have a sun-like star with 6 planets in tight, close-together orbits. Because of that, you frequently get multiple transits happening at the exact same time. The light dips just become this tangled, overlapping mess. Untangling a signal like this manually, to separate a real planet from background noise or just an instrument glitch, it takes an immense amount of time.
Which brings us right to Section 2, AI to the rescue. Enter Raven. This is a highly specialized piece of detective software built specifically to tackle that massive backlog of test data. The astronomical community basically fed it 4 entire years of accumulated information, and in one massive sweep, Raven successfully managed the detection and absolute confirmation of over 100 new exoplanets at once. Honestly, it's a monumental leap in efficiency.
Historically, astronomers have fought a constant battle against ambiguous signals. Binary stars, for example, can mimic the exact same light dip as a planet, which creates these really frustrating false positives. But Raven totally changes the game. It uses machine learning models trained extensively on highly realistic simulations. So having already seen millions of fake binary star dips and real planet dips, it validates signals with a consistency and a superior objectivity that the old manual approaches simply cannot match.
Moving on to Section 3, strange and rare worlds.
So, Raven confirms some truly bizarre planetary specimens out there. First, ultra-short period planets. These are worlds whipping around their host star so incredibly fast that they complete an entire orbit in less than 24 hours. Imagine celebrating New Year's Eve literally every single day. It also confirmed numerous tight multiplanetary systems, crammed close together in this delicate gravitational dance. And finally, it pulled rare specimens from a highly mysterious region known as the Neptune Desert.
Now, what's really interesting about this is that the Neptune Desert is a very real puzzle in astrophysics. It's a designated region close to a star where planets the size of Neptune are just inexplicably missing. We find huge Jupiter-sized planets there and tiny Earth-sized rocky planets. But mid-sized Neptune-like bodies, they're almost totally absent. So finding even a few rare specimens in this harsh desert using Raven is a massive win for understanding how solar systems actually evolve.
And Raven's massive data sweep also allowed researchers to nail down major planetary statistics with much greater confidence. Thanks to this AI analysis, researchers now estimate that exactly 10% of stars similar to our Sun possess a short orbit planet. And while this does align with previous theories, using AI has drastically reduced the margin of error. We are literally cementing these statistics into the astronomical record right now.
So the crucial point is this tiny fraction, 0.08%. Based on Raven's findings, this is the estimated percentage of sun-like stars that actually host a body in that mysterious Neptune desert. Less than 0.1%. This AI has given us a hard quantified measurement for just how incredibly rare this specific type of planetary zone truly is. It's turning abstract cosmic mysteries into precise, actionable data.
And finally, Section 4,
The future of exploration.
Ultimately, what Raven has handed the scientific community is a highly reliable new catalog of exoplanets, complete with the published software tools to navigate it. Astronomers no longer have to waste time pointing our most expensive telescopes at maybe planets. Now, they can deliberately cherry-pick the absolute most interesting, fully verified planetary systems for deep, intensive study.
And next-generation missions are already sitting on the launch pad. The European Space Agency is preparing its Plato mission to hunt for habitable worlds. Armed with a solid catalog built by AI and using these newly proven AI detection tools right out of the gate, what entirely new classes of planets will Plato discover? I mean, if an AI detective can find 100 hidden worlds in old data today, just imagine what it's going to uncover in the fresh data of tomorrow. Thanks for joining me on this explainer. Keep looking up, keep asking questions, and I'll catch you next time.